This is Leen and Joel, and we're here to talk about diversion today. Diversion is used in a range of industry applications. Based on frac focus data, we believe that diverters are used on about 5% of all frac jobs in the US. There's three main areas of application for diverters. First of all, on the perforation cluster level, to open more perforations and create more fracture complexity. Then there's application in the far field on the stage level, where we're hopefully creating fractures of similar length and minimizing the impact of direct frac hits in observation wells. And finally, in refracs, where we're creating fractures in areas that have maybe not been stimulated effectively before. We've got diversion covered at Liberty. We have a big toolbox with tools that cover everything but the kitchen sink in trying to provide our customers with effective diverters, mostly with the help of several of our vendors. And we're very big on field evaluating pressure and other things to determine if diversion is effective or not. The diversion toolbox is big. I'm not going to go through every individual item on this list, but again, we're going through three main areas of application, and each area of application requires its own type of diverter. And of course, a pressure evaluation before and after diversion is key to ensure diversion effectiveness. But Joel, in the next couple of slides is going to go through more detail on especially particular diverters.
I was going to talk to you today about diverter material selection, but then I realized really I'm going to talk to you about one chemical, and that's PLA, polylactic acid. At Liberty, we have several names for this material. It goes by DBA 65, DBA 75, or DBA 85. The reason I'm focusing on a single material is simply because in the most recent 5 to 10 years, PLA has really become the dominant chemistry utilized for frac diversion. Generally speaking, the reasons for this are its key attributes. Currently, it's relatively low cost versus its competitive products and can even be cut with sand in larger volume applications. It's considered green or renewable, and it comes from plants such as corn and sugar, and it's fully biodegradable. It has a low density relative to fluids it's being pumped in, which makes it easy to transport. It has high compressive strength, enabling it to withstand higher differential pressures relative to some other materials. It is self-degrading, meaning that once it starts to degrade, it goes to completion with minimal or no water contact. It degrades completely and leaves no damage. LOS testing has demonstrated 100% regain conductivity. It is generally compatible with frac equipment and fluids, and recently it has also become highly customizable in terms of geometry, specific gravity, temperature degradation, particle size and shape, and blend ratios. Due to this flexibility, it has evolved to replace many traditional diverter materials such as rock salt, benzoic acid flake, naphthalene, and ball sealers. So why is PLA the default favorite for practically all types of diversion in frac? One of the answers is in our ability to manipulate some key properties. Previously, this type of polymer manipulation technology hasn't been appreciably applied in our industry, possibly due to limited usage rates or possibly higher material costs. I really can't say. It can definitely be said that one of the key drivers for PLA at the moment is price. Yes, we are definitely in a low-cost PLA environment relative to the past. Since diversion is more of a physical phenomena than a chemical reaction, most of the beneficial properties of PLA that are being exploited can be accomplished by using other polymers on the market. One of the more unique properties of PLA, however, is its degradation behavior, which is influenced by temperature, pH, water, TDS, sample morphology, and molecular weight. The particle degrades via hydrolysis, where water is used to break down the long-chain polymers into smaller components. It is a self-degrading and self-catalytic, meaning that the rate of degradation actually accelerates with time. The degradation goes to completion to leave lactic acid and is non-damaging. Smaller particles do not hydrolyze at increased rates. As you can see on at the chart to the right, we can achieve many different rates of degradation using essentially the same material. So what are the available properties and ranges for this material? The material's geometry can obviously be altered. Typical grind sizes utilized in frac range from 200 mesh to some far field applications to 6 to 8 mesh used to initiate bridging on the perforations. But the material can be purchased down to 2500 mesh or 5 micron. Different types of flake product are also available. Varying degrees of sphericity and roundness are available. Custom grind sizes can be manufactured, and custom blend rates of any of these products can be optimized for both transport and bridging and are readily delivered to the field. The density of the material can also be altered. If desired, the specific gravity can be lowered by increasing the porosity, as can be seen on the microscopic image to the right. The typical specific gravity of PLA is around 1.25 Sg. The lowest density to date has been around 0.9 Sg. Perhaps most importantly, for frac, the morphology or structure can be manipulated. The polymerization process can be controlled to yield more crystalline or more amorphous material. This means that custom options available for high temperature, longer lifespan applications are available. Why is the morphology of your PLA important? Because the morphology controls the chemical and mechanical properties of PLA. And it's manipulated in 3 primary ways. First, the molecular weight. The molecular weight is the primary driver behind the rate of hydrolysis. Second, the degree of crystallinity. The degree of crystallinity is the primary driver of mechanical properties, particularly how the properties change with increasing temperature. The third way PLA morphology is manipulated is via the monomer content. Generally, there are 3 lactide monomers used to make PLA: L-lactide, D-lactide, and mesolactide. The ratio of each of these in the final polymerized product affects the reactivity with agents such as its tendency to copolymerize with FR and metal cations. Because this also affects crystallinity, it has some influence on the mechanical properties. So for example, if you want a soft polymer to place at low rates and pressures that can survive in a high temperature environment, you would look for a high molecular weight amorphous polymer. If you want something for low temperatures that must support higher pressure differentials in open hole frac treatment, for example, you would look for a low molecular weight semi-crystalline variant. So what are the ways that we test for performance of our diverters? The most basic testing that we do is hydrolysis or degradation testing. This helps us to confirm the material will be gone in a defined time frame using your specific conditions such as temperature and water type. This can be done either static or dynamic. Additional testing can be done using what is known as a permeability plugging cell using a variable diameter slot plate. This type of testing helps us to optimize blend rate ratios and ensures that bridging will occur across the specified gap. Further performance testing can be completed upon request, such as maximum pressure differential testing or modified fracture conductivity cell for far field behavior. In summary, PLA has recently become a popular choice for diversion and hydraulic fracturing applications. The primary drivers for this are both price and alterability of its primary properties.
An engineering evaluation of diverters is key because diversion doesn't work the same way in every field or formation or reservoir. At Liberty, we have a variety of tools available to evaluate the impact of diverters. For example, we can look at pressure before and after, look at injectivity, conduct step-down tests to determine how many perforations are open. We can evaluate other diagnostics such as tracer and use fiber optic data. And we can, for instance in well watch, look at the timing or the volume needed to hit an offset well. We'll let the data speak as to what works best in what area of applications to help you select the best diverter for your application.
I want to give a special thanks out to Nick Koster for helping me with diverter technology.
Thanks, Nick.
This has been Joel Siegel.
He's Liberty's Lab Rat, and this was Leen Weijers.
He's Liberty's top nerd. For more information, please visit libertyfrac.com.